Calculus is coming. Welcome back to Calculus 2. In this lecture, we're going to get to probably the most difficult part of Calculus 2 with an integration method called partial fraction decomposition. I will tell you in advance, this is not difficult for calculus reasons. This is difficult because most of your algebraic skills have atrophied. There's going to be a ton of algebra within this lecture and topic. So if you at all encounter any difficulties at any point, it's likely algebraic difficulties, not calculus difficulties. So I'll try to re-emphasize and remind you of that as we go. So with that out of the way, let's go ahead and get to partial fraction decomposition. All right, and what this is a method for integrating fractions or expressions that are fractions. In mathematics, we call those rational functions if you want to be technical. So these are going to be basically simple expressions, ratios of polynomials. We'll give some definitions in a little bit, hopefully some familiar terms for polynomials, degree of a polynomial, all that stuff. All right, but I want you to consider these examples here. And then maybe algebraically, thinking back to algebra, which might have been a long time ago, what they might look like. Now, our goal is to basically evaluate these integrals. And we're going to try to use kind of a mathematical problem-solving technique that if we have a difficult problem, we'll try to do something to it to convert it to a simpler one that we can solve. And what we're going to do here is rewrite this rational function that we're given as some sort of combination of simpler functions. Now, simpler is subjective, but we're going to be simpler fractions. So let's get into where you might have encountered this in algebra. We'll come back to calculus in a little bit. All right, so what I'm going to do right now, just to test your algebra skills, is this seemingly simple problem of subtracting these two fractions. So pause the video. Give yourself about a minute. We'll check in. All right, now hopefully this was straightforward for you. If you struggle with this, reach out to either myself or your professor to make sure you can go through this very quickly. So here we can just subtract or add fractions using a common denominator, and we should get this simplified result, multiplying out the factors in the denominator. Now, just in case you're a little rusty, maybe your Calc 1 course was a while ago, and then you had Calc 1, pre-calc, and algebra in succession, and then you took a gap from then to taking Calc 2 now. Well, let's just go through the work. I'll put it up, pause the video so you can digest it, but to get a common denominator here in LCD, we just basically multiply the two denominators, x minus 2 times x plus 3. Multiplying your denominators usually gives you the least common denominator for simple fractions, I'll say. All right, the rest of it is just multiplying and dividing by the missing factors, and then being careful with parentheses there because we have minus x minus 2. There's a double negative there, subtracting a negative. So this should be pretty straightforward. Now, what's the point of this? Well, the direction going from the left side to the right, that's an algebra topic. You can combine those two fractions to a single one going from the expression on the left to that on the right side by using a common denominator. You went through that in detail in your algebra course, if you can even remember that. Now, also an algebra topic, but usually not taught, it's really delayed to now when you need it in Calculus 2, is the opposite procedure, taking a single fraction and then splitting it apart to those two fractions on the left. That procedure or process of splitting apart, the opposite of combining with a common denominator, is called partial fraction decomposition. Now, this topic can be taught in algebra, but there's really not a reason for it. You don't use it typically until you reach Calculus 2, with a method for integrating rational functions. All right, so that's just algebra. Let's go back to calculus. Pause the video, write this example down, the two fractions being subtracted equaling the single fraction on the right side. All right, now let's take this algebra problem and turn it into a calculus problem. That's what you're all here for, right? You're experts on algebra. You'll find out soon enough. Let's get to a calculus problem with this. Okay, and what we have here is the integral of the end result from before. All right, we're now learning about our goal for this lecture. Here we have an integral of a rational function, an integral of a fraction. All right, and what I want to convince you is we can basically integrate this. What we did with our algebra problem a few minutes ago was take those two fractions, subtract them to get that single fraction. Now we're going to reverse this for our use now with integrating. We have now expressed this complicated function as simpler functions that we know antiderivatives for. Now, you might be thinking, wait a second, I don't know an antiderivative for 1 divided by x plus 3. Well, what if I told you you do? What's the antiderivative for 1 over x? Any guesses? It's pretty natural. It's natural log. So if we use a u substitution, both of these fractions convert to 1 over u. They'll integrate to natural log of u, and then we back substitute. So the integration is actually very quick. What we have to address is how we go from that single fraction and express it as the difference of those two fractions there. How do we do that? That process is what we're going to learn about. That's called partial fraction decomposition. So most of our lecture is going to be spent on just learning how to reverse combining fractions, learning how to do a partial fraction decomposition. The calculus, as we mentioned in the first few seconds, is actually very minimal. Most of our lecture and examples are going to be spent going through algebra. All right, now on the topic of other integrals, hopefully you recognize in this, this problem the antiderivatives for 2 divided by x minus 2 and the antiderivative for 1 divided by x plus 3, both integrate to natural logs. There are some other integrals frequently encountered in problems in this lecture that I want to make you aware of. So at the top there is our 1 over a shortcut. We'll be encountering this all over the place within the first few parts of this lecture. Another one is a natural log in disguise. It involves x squared in the denominator, but the numerator has an x in it. You can do a substitution for that second integral formula. U equals x squared plus a squared. Substitute the derivative of x squared plus a squared gives you a factor of x for the differential du, and that should be a piece of cake to work out. So we have the first two integral formulas there are functions that integrate to logarithms, to natural logs. Make sure you're comfortable with those. We will see those frequently. Another one, which we mentioned a few different times, as early as substitution, and most recently when dealing with trigonometric substitution, is this integral, which gives an inverse tangent. This is going to be incredibly useful later on in some topic for this lecture, a part of partial fraction decomposition. And it's the key to making the calculus minimal. Make sure you know this third integral. We'll be seeing that in examples and referencing how to use it. A in that expression is a constant. All right, and then our last integral down there, 1 divided by ax plus b squared, that you can evaluate using a u substitution. U equals ax plus b. All right, so before advancing, make sure you're comfortable understanding and being able to work out all 4 of these integral formulas. If you can do that, you're probably in good shape for the calculus involved in this lecture. The algebra is another story. Every calculus student thinks they're great with algebra, a 3rd degree black belt in algebra. That's far from the truth. Many quickly find their algebra skills aren't nearly as good as they thought, which we'll be getting to pretty much right now. All right, so let's start to get to definitions that we're going to need, and there's some technical things related to polynomials and rational functions that we need to be aware of for our purposes right now, applying partial fraction decomposition to evaluating integrals. All right, so a definition is a rational function. It's a ratio of polynomials. The notation we'll stick with for this lecture, fairly standard. A function f of x is a rational function, p of x divided by q of x, if both p and q are polynomials. So make sure you're comfortable with polynomials. We have some examples here of 3 different rational functions. All right. One quantity for a polynomial that we're going to need is the degree. So you can, very loosely say the degree of a polynomial is the highest exponent, but a little more technical, it's the highest power or exponent of x with a non-zero coefficient. All right, so just an example, we have that polynomial at the bottom there, p of x equals 2x to the 4th minus 5x cubed plus x squared minus 3x plus 4. The degree of that polynomial is 4, or we would say this is a degree 4 polynomial. All right, again, all probably basic. In order for us to apply partial fraction decomposition, we have to understand that there could be 2 types of rational functions. All right, the first type is what we were going to call a proper rational function. This is like a proper fraction where your numerator is less than the denominator, like 3/4. We would say 3/4 is a proper fraction. But now for rational functions, we have to quantify numerator and denominator, their size, by degrees of their polynomials. So we define a proper rational function as a rational function where the degree of the numerator is less than the degree of the denominator, strictly less. An improper rational function, just like an improper fraction, for instance, 5/4, there the numerator is bigger than the denominator. An improper rational function is one where the degree of the numerator is greater than or equal to the degree of the denominator. All right, degrees just talk about the highest power, the degree of the polynomials. Proper rational function, the denominator has the highest power. An improper rational function, the numerator contains the highest power, or the powers within the numerator and denominator, the degrees are equal. All right, so we have on the screen here an example of a proper rational function, this function g of x. Notice the degree of the denominator is 3, the degree of the numerator 1. So the denominator here having the bigger power, bigger degree, makes g of x a proper rational function. H of x now, where the numerator is a degree 3 polynomial, notice for h of x, the denominator is written as x squared plus 2 squared. Hopefully you can see, if you were to multiply that out, the highest power of x would be x squared. So this one's improper. Numerator of h is a degree 3 polynomial. The denominator of h is a degree 2 polynomial. All right, all pretty simple. Why are we bringing up proper versus improper rational functions? All right, well, I have to make you aware, pretty much everything we're going to learn about partial fraction decomposition, which we haven't gotten into yet, that can only be applied to proper rational functions. So if the rational function is improper, we need to use long division and basically rewrite this in terms of a remainder. So the expression r of x, r is the remainder. And then the remainder has a degree less than what we were dividing by. All right, so there is a necessity for polynomial long division. We're going to minimize that within this lecture since it doesn't come up that often, there's a few examples scattered in the homework, but those are best left for specific questions if you kind of forget or if it's been a while since you've done polynomial long division. It's not complicated, but it's often forgotten. All right, we want to focus on new stuff and all the kind of typical places Calculus 2 students will struggle, which we'll be focusing on within all of our examples within this lecture, part 2 of this lecture, and there's a part 3. That's how complicated all this gets. All right. So with that out of the way, let's go through an overview just so we have some guidance. I always like to do this at the start of a new topic or lecture, just so you have some idea where we're going. All right, so our ultimate goal is to learn how to evaluate an integral of a rational function. So we're integrating a rational function, p of x divided by q of x, where notation, we're going to assume p and q denote polynomials. All right, now this probably seems simple. How complicated can this get? Well, depending on your algebra skills, it could be quite complicated. Everything we'll learn about partial fraction decomposition in the next few minutes and part 2 and part 3 of this lecture, the starting place pretty much for every integral is to completely factor the denominator. The numerator doesn't really matter so much. Everything related to partial fraction decomposition depends on the factorization of the denominator. So we're going to emphasize that as we go through problems. So we have some typical factorizations here. Q of x denoting our rational function's denominator. Here's some standard factorizations. Now again, just so you're aware of where typical problems lie, factoring could be a problem for a typical Calculus 2 student. If you feel at all weak on factoring, that's a great thing to ask during office hours and follow up on. All right. To guide us through the different parts of partial fraction decomposition, let's take a look at those typical factorizations. There's 2 types of expressions. Take a look at the example 1. We have factors x plus 2 and x plus 3. Those are linear expressions. In example 3, we have a factor of x squared plus 4. X squared plus 4 is a quadratic degree 2 polynomial. Now, if that were x squared minus 4, x squared minus 4 is a difference of squares, that factors. X squared plus 4, a sum of squares, doesn't factor. So if a polynomial doesn't factor, mathematically, the technical term for that is that polynomial is then said to be irreducible. Irreducible means doesn't factor, unfactorable. Okay, so there's 2 types of factors within these examples. There's the linear factors, and then there's the irreducible quadratic factors. Now, you might have never learned about the fundamental theorem of algebra, but it's important, hence why it's called fundamental. And what it basically says is every polynomial with integer x coefficients over the real numbers, so in other words, if you only are allowed to use real numbers, every polynomial can be factored into a product of linear factors and irreducible quadratic factors like we have here. All right, we're going to mention this again, but this is a good place to point out the standard approach to teaching and learning about partial fraction decomposition. There's 2 types of factors, linear factors and irreducible quadratic factors, but there's 4 parts. Each of those types of factors, notice in example 2 there, we have the factor x minus 1. That exponent 2 tells you x minus 1 is a repeated linear factor. So we have 2 types of factors, linear or irreducible quadratic factors. Each of those types could be distinct, not occurring again, or unique, or they could be repeated. So we have in total 4 possibilities: distinct linear factors, repeated linear factors, distinct irreducible quadratic factors, and repeated irreducible quadratic factors. Unfortunately, not only is this the standard labeling, but the labels here, as the numbers go up for those different parts, the difficulty increases with them. So part 1, distinct linear factors, is pretty simple. Part 4, repeated irreducible quadratic factors, is awful, but we're going to learn about it anyway. All right, let's proceed to part 1. So for right now, the remainder of this lecture, part 1, we'll be focusing on linear factors within the denominator that are distinct. There's no repetition within a single denominator for any factors. Okay, so let's start first with the form of a linear factor. It takes the form, like you saw from algebra. Think of the equation of a line, y equals mx plus b. We just change m to a. So a linear factor is of the form ax plus b, where a and b are constants, numbers. Typically, they're going to be integers. All right, now here we have to get a little abstract, which as a Calculus 2 student, you're probably okay with. Let's suppose we have a denominator, q of x, that has been factored with n distinct linear factors. Here, each of the two unknowns for the linear factor, we have it as a1x plus b1. Each linear factor has two unknowns, two constants. But we have n factors. We're going to assume none of these factors are repeated, so we're going to assume these are distinct. Now, each different type of factorization in your denominator dictates a certain form for the partial fraction decomposition. If that's the factorization for our denominator, q of x, written as that product of n different linear factors, then beyond the scope of our course of kind of understanding why this works, but it works, the partial fraction decomposition for the associated rational function takes the form for each factor in your denominator. Let's focus on the first factor, a1x plus b1. We get a partial fraction of the form, a constant a1, capital A1, divided by the linear factor, a1x plus b1. And for each factor that's linear in your denominator, we get a related partial fraction. They all have the form a constant divided by that matching factor. All right, I realize this might be abstract. Most students don't really grasp this. They really get it when we take a look at specific examples, which we'll be looking at, but this is the standard language for mathematics in the calc sequence and what comes next. So I want to make sure you are comfortable with that. All right, now our goal here, keep in mind, the factorization is giving us a1, b1, a2, b2, all the way up to an, bn. Our goal now is to solve for the unknowns, capital A1, capital A2, down to capital A sub n. Now, typically, we're not going to use subscript notations. This is just a general way in mathematics we use to denote an arbitrary finite number of quantities. Typically, we're going to be looking at 3, 4, 5, at most 6 unknowns. So we'll label them typically A, B, C, D, however many we need. Okay, so for each factor in your denominator, you get a partial fraction, an unknown constant divided by the linear factor. And what this will give us is n unknowns. And to solve, we need the same number of equations as we have unknowns. That's where the algebra comes in, why it's so involved, which we'll start to see. All right, so let's get to some examples on writing out the partial fraction decomposition. All right, pause the video and give this an attempt. I realize that general explanation we gave probably might not help. you might have to wait to really get it until we go through this, but give yourself a few seconds and we'll check in. All right, ready? What I want you to notice is the factors within the denominator. The factors here are x minus 3 times x plus 4. All right, and we have two linear factors, so we get two partial fractions. Some unknown, capital A, divided by x minus 3, plus another unknown, b, divided by x plus 4. That's it. Our goal with this example then would be to solve for what a and b are. That's part of the partial fraction decomposition process, which we'll be getting to. All right, now things might be sinking in. Let's take a look at a second example. Pause the video and we'll check in a few seconds. All right, just think, how many factors do you have in your denominator? 3. Your factors, which are all linear, are x, x minus 1, and x plus 2. You have 3 factors, so you get 3 partial fractions. A over x, b over x minus 1, and c over x plus 2. 3 linear factors give you 3 partial fractions. Okay, so there's really not much to distinct linear factors. Now, the benefit of this being our first starting place to start is the integrals we get are actually really simple. And we already mentioned in the beginning, we're going to typically be seeing integrals that give natural logs. Pretty much all linear factors in a denominator, when we have it of the form 1 over the linear factor, 1 over ax plus b, they always integrate to a natural log. What we're going to have to learn and deal with is how do we solve for the constants involved, a, b, c, however many we need. Typical problems will involve usually 2 to 6 different unknowns to solve for. That's what we'll be getting to momentarily. All right, now the standard approach to solving for the constants, most students struggle with equations involving fractions. So I'm going to advocate that we're just going to try to eliminate fractions. Recall you can do that when you have an equation involving rational expressions, denominators. Just multiply the whole equation by the LCD. If you have the correct LCD, least common denominator, all the factors in every denominator should cancel out. So you can always eliminate fractions. All right, hopefully this is all starting to sink in, but it might not all sink in until we take a look at a complete start to finish example. All right, and with that out of the way, let's get into it. Now, I do want you to expect for all the examples in this lecture, there's going to be a ton of algebra, but fortunately, that's not for part 1. Part 1 being distinct linear factors. The algebra really starts to increase in the second, third, and fourth parts. All right, so right now think of this as the calm before the storm. All right, let's get to example 1. All right, now I would like you to try some of this. So pause the video. I'm going to keep the steps for solving an integral using partial fraction decomposition up on the screen at the start of every example, since these are definitely lengthy problems. They're multi-parts, as you see here. So give yourself an attempt. The starting place in step 1 is to completely factor the denominator. See where you can go from that. We'll check in a little bit. All right, ready to go through this? All right, let's go through it. Starting place, let's factor the denominator. That should go pretty quick. Numbers that multiply to 10, but add or sum to -7, -2, and -5. So your factorization would be x minus 2 times x minus 5. All right, that's our denominator. So we're going to rewrite that original fraction or rational function with the factorization there. Now that we've fully factored our denominator, we notice here we have two different distinct linear factors. We can now perform a partial fraction decomposition. And that's just writing out what the decomposition is. Each linear factor gives us a partial fraction, a constant divided by that linear factor. All right, and that is the partial fraction decomposition for a rational function where the denominator contains distinct linear factors. All right, now the rest of it from here is we're going to have to solve for the two unknowns, A and B. All right, so what I would like you to do is take a look at a left and right-hand side as an equation. So let's take a look at the rational function with the factor denominator. Think of that as the left side of your equation. The right side of the equation will be the side with the partial fractions. All right, now we're going to multiply both sides by the LCD. I'm taking my time, so that way the algebra isn't coming out of nowhere. All right, so we're going to multiply both sides by the LCD, which is x minus 2 times x minus 5. We multiply both sides by that. Recall your fundamental rule of algebra: what you do to one side, do to the other. So multiply both sides by the LCD. You can see on the left side, those factors completely cancel, leaving you with 1. On the right side, in red, the LCD, x minus 2 times x minus 5, we distribute that in through the brackets. And when you distribute that in, one factor at a time cancels out. Either individually, x minus 2 cancels on the term involving A, or when you distribute it to the term involving B, it's the x minus 5 that cancels. Now, if you've done this correctly, you should find there's no more fractions. So you hopefully are comfortable multiplying each side by the LCD and then it reducing down to this. This is going to be our starting place for solving for the constants A and B. All right, pause the video to let that sink in. We're going to kind of rearrange the work just to fit this all on kind of one page. All right, so I'm just rewriting that end result there. And what we're going to do is a very simple approach to solve for A and B. Mathematically, what we have here, a partial fraction decomposition, we're going to think of it as an identity. In other words, it's an equation that is true for every value of x. Now, the advantages of thinking of this as an identity is we can plug in any value for x. One of the nice things about the case of distinct linear factors is that every linear equation has a solution. So we're going to choose appropriate values for x to make each linear factor individually evaluate to 0. So basically just think, what value of x can I plug in to make each linear factor become 0? Well, here we have two values. Plug in x equals 5, and then plug in x equals 2. All right, you could again pick any values for x that you want, but these values, 5 and 2, individually make one of the factors 0. So it'll be very easy to solve for A and B. That always happens in the case for distinct linear factors. All right, let's plug in x equals 5 to both sides of this equation. Notice, since our numerator was 1, our left side of this equation has no x for this example. In general, after you've eliminated fractions, your left side could have an x in it. So you plug it in there as well. We don't have one here, but Just be aware of that. So in that equation, plug in x equals 5 everywhere. You should be left with this resulting equation, 1, that's the left side. 5 minus 5 is 0, so the term with a drops out. And then you're left with b times 5 minus 2. I think 5 minus 2 is 3. I checked with my calculator before recording the lecture. So we get the equation 1 equals 3b. Solve for b, divide by 3. We get b as 1/3. Now solving for a is equally fast. We just plug in x equals 2. We get the equation 1 equals negative or minus 3a. Divide by negative 3, and we get a as negative 1/3. Complete coincidence here, but it happens a lot. But don't think it always has to happen, that your values for a and b have to be the positive and negative versions of each other. Happens a lot, but it doesn't have to happen. Okay, so we've solved for a and b. Let's plug them back in above to the partial fraction decomposition. So we're just going to replace a with negative 1/3 and b with positive 1/3. Now, since a and b are fractions, and we already have partial fractions, let's not have fractions within fractions. Let's pull the negative 1/3 and positive 1/3 out front. All right, and what we've done is express the original function in a form that's more easily integrated. Each of those partial fractions integrates to a natural log. So we now rewrite our integral using the partial fraction decomposition. And the integration is very quick from here. It's actually longer to do the algebra than it is to do the calculus. Kind of interesting, right? So we integrate here. 1 over x minus 2 integrates to natural log of x minus 2. And 1 over x minus 5 integrates to natural log of x minus 5. The negative 1/3 and positive 1/3 are just constant multiples. So we get our antiderivative, and that's it. Now, there's really not much to the case for partial fraction decomposition, part 1. The case of distinct linear factors. Most of the work occurs in part 2 and beyond, repeated linear factors, and then the 2 parts dealing with irreducible quadratic factors, which we'll kind of be getting to immediately after this with part 2 of this lecture.